We will now try to derive the expression for maximum torque. When will maximum torque occur? When there is maximum power. So if you remember the equivalent diagram, equivalent circuit, this is VTH. We have gotten RTH and XTH, R2 dash by S, and finally JX2 dash, right? This is the equivalent circuit. Now the torque, induced torque, we know this is equal to the air gap power divided by the synchronous speed, okay? So if T induced has to be maximum, then PG has to be maximum. What is PG? It is the power dissipated in this resistance R2 dash by S, okay? So by maximum power transfer theorem, if you see, maximum power will be delivered to R2 dash by S when the rest of the impedance, that means looking through these terminals, the rest of the impedance, they are in series. So the impedance should be equal to this resistance value, the magnitude of the impedance. So what is the impedance that we have? RTH plus J times XTH plus X2 dash. So the magnitude of this should be equal to R2 dash by S, okay? So that means R2 dash by S is equal to root over RTH square plus XTH plus X2 dash whole square. This is where the maximum slip will occur, okay? So you can write the expression for maximum slip. This is equal to R2 dash divided by root over RTH square plus XTH plus X2 dash whole square. So this is the value of slip at which maximum torque occurs. So now this expression you need to substitute in the expression for induced torque. What is the expression for induced torque? We have seen T induced is equal to 3 by omega S VTH whole square into R2 dash by S divided by RTH plus R2 dash by S whole square plus XTH plus X2 dash whole square, okay? So if you simplify this expression, what are you going to get? T induced is equal to 3 by omega S into VTH square R2 dash by S divided by RTH square plus 2 RTH R2 dash by S plus R2 dash by S whole square plus XTH plus X2 dash whole square. But we know that at the maximum torque condition, R2 dash by S is equal to root over RTH square plus XTH plus X2 dash whole square. So that means these two terms here we can write R2 dash by S whole square, okay? So you're going to get 3 by omega S into VTH square R2 dash by S divided by 2 times RTH R2 dash by S plus R2 dash by S whole square. Finally, if you substitute R2 dash by S is equal to in terms of RTH and XTH, what are you going to get? T induced is equal to 3 by omega S into 0.5 VTH square divided by RTH plus root over RTH square plus XTH plus X2 dash whole square, okay? So this is the expression for the maximum induced torque. Now one interesting observation that you can see here is the induced torque is independent of the rotor resistance R2 dash. R2 dash is nowhere in the expression, okay? And here in the maximum slip, the slip at which maximum torque occurs, not the maximum slip. In this expression you can see R2 dash is there only in the numerator. That means S max is directly proportional to R2 dash. What is the effect of this? We can change the slip at which maximum torque occurs by changing the rotor resistance. But we cannot change the torque itself. The value of the maximum torque itself will remain the same. Okay. So if you see the characteristics, it will become more clear to you. Let us say this is the torque axis and this is the speed axis. Slip is increasing in this direction. Okay. Now at one particular slip, let us say this is the characteristic. Okay. Let us say this is R2 dash and this is where S max is. Slip at maximum torque. Now when you increase the resistance, what will happen? The S max is going to increase. So that means it will move to this direction. The peak will move in this direction. Okay. So that means this is the new characteristic. You can see here, finally it will reach at this point only, because what is this value of speed? The synchronous speed. Okay. So this if you take as R2 dash, you can take R2 dash A, R2 dash B. So here R2 dash B is greater than R2 dash A. Okay. So as resistance increases, the torque, the maximum value of maximum torque will remain same. This is the important point here. This is the torque axis. Okay. Further, if you increase the rotor resistance, further the maximum torque is going to shift here. Okay. So at one point, the maximum torque will become the starting torque. Okay. So that means this is how the torque characteristic is going to look like. R2C dash, if you take, this is going to be higher than both the resistances. Okay. So from here you can see that by increasing the resistance, we can actually increase the starting torque. If you can see here, for R2A dash, starting torque is here. With an increase in rotor resistance, the starting torque has improved. So this is the torque slip variation in torque slip characteristics with a variation in the rotor resistance. Next, what is the expression for starting torque? Starting torque means simply you have to substitute S is equal to 1. So what will you get? T induced at start. This is equal to 3 by omega S into VTH square R2 dash by S. S is equal to 1. And here you are going to get R2 dash RTH plus R2 dash whole square plus XTH plus X2 dash whole square. Now what about maximum starting torque? That means we have seen the characteristics. If this is the characteristic at a particular resistance, then if you increase the resistance, then this maximum value is going to be obtained at the starting itself. So what is the condition for this point? That means what is the value of resistance wherein the maximum torque is occurring at the starting itself. Okay. So the maximum starting torque will occur when S max is equal to 1. But we know S max is equal to R2 dash divided by root over RTH square plus X2H plus X2 dash whole square. This is equal to 1. This means that R2 dash should be equal to RTH square plus XTH plus X2 dash whole square. So this is the condition of rotor resistance wherein the starting torque will be the maximum torque. Now for easy analysis, often we do some approximations. Okay. So if you remember this Thevenin's equivalent circuit that we have derived, VTH, RTH, JXTH, and here we have the rotor R2 dash by S and JX2 dash, right? Now if we assume the stator impedance to be negligible. Approximation is that stator impedance is negligible. Okay, that means R1 is equal to 0 and X1 is also equal to 0. Now what is this RTH and JXTH? This is given by, if we take as ZTH is equal to RTH plus JXTH, this is equal to R1 plus JX1 in parallel to JXM. Okay, so a 0 impedance, that is a short circuit in parallel with another impedance. What will it be? It will simply be 0. Okay, so ZTH, that is equal to RTH plus JXTH, it will become equal to 0. Then what about VTH? This was JXM divided by R1 plus J times X1 plus XM into the supply voltage V1. Similarly, if you substitute R1 and X1 is equal to 0 here, what you are going to get? Simply the supply voltage V1. You can write here supply voltage. So that means if we assume that the stator impedance is negligible, then we are going to get VTH is simply equal to V1 and ZTH is equal to 0. Then what will be the rotor current here? This is I2 dash. The rotor current referred to the stator side. What will it become? I2 dash is equal to V1 divided by R2 dash by S whole square plus X2 dash whole square root over this. So this is one equation. Now what about the induced torque? T induced is equal to the air gap power divided by the synchronous speed. Now PG is the power dissipated in R2 dash by S resistance. So you are going to get 3 I2 dash whole square R2 dash by S. The same derivation, right? We are using 3 times because this is per phase loss, per phase dissipation. So 3 times into that per phase will give you the total air gap power. So this, if you substitute I2 dash value here, the final expression you are going to get 3 by omega S into V1 square R2 dash by S divided by R2 dash by S whole square plus X2 dash whole square. This is the expression for induced torque. You can encircle each of these expressions. Now what about the slip at which maximum torque occurs? We know that S max is equal to R2 dash divided by root over RTH square plus XTH plus X2 dash whole square. Now RTH and XTH is equal to 0 with the given approximation. So we are going to get S max is simply equal to R2 dash by X2 dash. Now these are the parameters that are referred to the stator side. If you express in terms of the actual parameters, then also you will get R2 by X2. Okay, because the transformation ratio that you use to refer to the stator side, both of them will be cancelled because one is in the numerator, other is in the denominator. So that means the maximum value of torque will occur at a slip when it is equal to the ratio of the rotor resistance divided by the rotor reactance at standstill. Standstill in the sense when it is in the locked rotor position. Then S is equal to 1 and reactance will be X2, right? So S max will be equal to the ratio of rotor resistance divided by the rotor reactance at standstill. This is the approximate value of slip at which the maximum torque will occur. Okay, so this is the third equation. Finally, we can get the values of maximum torque and starting torque. T max is equal to, you substitute the value of S max, equation 3 in equation 2. The final answer I am writing, you are going to get 3 by omega S into 0.5 V1 square divided by X2 dash. This is the expression for maximum torque, equation 4 if you take. And starting torque also you can write T starting torque is nothing but when S is equal to 1. So, S is equal to 1 if you substitute in equation 2, then you are going to get 3 by omega S into V1 square R2 dash divided by R2 dash whole square plus X2 dash whole square. Okay. So, these are the various approximations, various values you will get once you do this approximation of neglecting the stator impedance. Now, we can do some further approximations as well. So, what are the further approximations? If you remember, we have discussed that the torque slip characteristics, if you see, the region of operation is a very narrow region. Okay, this is the characteristic, right? Now, this is the region where we operate, and this region is considered to be almost linear. Now, this is the synchronous speed, and this is the region where the slip is low. So, it's the low slip region. So, under low slip conditions, R2 dash by S, this will usually be much greater in magnitude than X2 dash, because S is a very small value. R2 dash by S will become a very large value. Okay. So, this is the approximation that you can consider. Now, what is the result of these approximations? We can simply ignore the resistance X2 dash because they are in series. See, we have neglected ZTH, RTH and XTH are 0. So, what was left out? R2 dash by S, and this is X2 dash. Now, this is the current I2 dash. Now, what was the voltage? The supply voltage was given here, V1. Now, since this is becoming negligible because of the approximation under low slip region, then what you are going to get? The current is equal to I2 dash is equal to V1 by R2 dash by S, or you can write S V1 by R2 dash. In this case, what will happen to the induced torque? T induced is equal to 3 times I2 dash whole square. So, this will be S V1 by R2 dash whole square into R2 dash by S. So, you are going to get induced torque is equal to 3 by omega S into S V square divided by R2 dash. So, this is a very important expression. It will give you a very easy relationship of the induced torque in terms of the supply voltage. Okay. So, this is V1. You can see that the induced torque is directly proportional to the supply voltage. You can write this point down, it is very important. T induced is approximately proportional to the square of the supply voltage. Okay. So, this is the approximation of low slip operation. This is where we operate. So, this approximation is also valid. Finally, one more point which will be useful when you are solving problems. We know the induced torque expression is 3 by omega S V square by, we are talking about the approximation, okay, V square by R2 dash by S whole square plus X2 dash whole square into R2 dash by S, right. This is at some slip S, some value of S, okay. Now, what is the maximum torque expression? This is equal to 3 by omega S into 0.5 V square by X2 dash. This is at S max is equal to R2 dash by X2 dash. So, from both of these expressions, we can get any torque as a fraction of the maximum torque, okay. So, the ratio T by T max will be equal to 3 by omega S and V square will be cancelled out. So, what we are going to be left out with? R2 dash by S divided by R2 dash by S whole square plus X2 dash whole square divided by 0.5 by X2 dash. Now, what we will do is, instead of R2 dash, we will write S max X2 dash in this expression. Okay. Then you are going to get S max X2 dash by S divided by S max X2 dash by S whole square plus X2 dash whole square divided by 0.5 X2, we can write as X2 dash by 0.5. So X2 dash will be cancelled. Finally, if you simplify, you are going to get 2 by Sm by S plus S by Sm. Okay. So T by T max will be equal to 2 by Sm by S plus S by Sm. Okay. Where what is S? S is the slip at this particular torque.